Hello, in this video we will review the concept of functions and mapping. More precisely, we'll talk about function, we'll talk about a domain of a function, the codomain of a function, the range and the image of a function. We'll talk about what it means for a function to be injective or one-to-one, or we'll talk about what it means for a function to be surjective or onto. We'll talk about what it means for a function to be bijective. We will define the inverse of a function. We'll talk about the identity function. We'll talk about preimage, compositional functions, associativity, and commutativity. Okay, so what is a function? A function is, which we will denote little f, is simply a map from two sets. So a function f from a set x to another set, say y, is a rule or a process or a procedure which assigns to every element little x in the set x a value or an object which we will call f of x in y. So for instance, let's look at this function here, x. The set x, big X, contains 4 elements, x1, x2. The set y contains 6 elements, y1 through y6. And let's suppose we send x1 to y1, and let's suppose we send x2 to y2, x3 to y3, and let's say x4 to y4. So then y1 becomes f of x1 because it's being mapped, because x1 is being mapped to it. Y2 becomes f of x2. Y3 becomes f of x3. And y4 becomes f of x4. Now, the collection containing these 4 elements is, this collection here is called the range. This is the range of the function f. And now, so to be precise here, we saw that for every x in big X, we assign a value to x, which we call f of x, denoted f of x. Now, the domain of every such element, little x, is big X. So what is the range? The range of f is the set containing all f of x such that little x is in the domain of the function. So simply put, the range contains everything that you obtain through this assignment. And the image of an element little x in big X is f of x. So one can actually go a little further and say that, and say the following: we may regard a function simply as a collection of all ordered pairs of the type of all other pairs of the type x f of x such that little x is in some set x. This can be used to also define what a function is. Now, when do we say that two functions are equal? When two functions, say f and g, equal. This is the case if we say two functions are equal if so two functions will say that f is equal to g if and only if they have the same domain, the same codomain, and moreover for all x and y in for all x and y for all x in the domain of f and g, we have equality. That's f of little x is equal to g of little x. Let f be a function from x into y. Here x is the domain of the function and y is the codomain of the function. We say that f is injective or one-to-one if the following holds true. Given x and let's say x prime in the domain, if x is not equal to x prime, then f of little x is not equal to f of x prime. Also, this definition can also be is equivalent to the following. So you can also use the following. If given little x and x prime in x, if f of x is equal to f of x prime, then x must be equal to x prime. Okay, all right. So notice that the second statement is the contrapositive of the first statement, and since an implication in its contrapositive are logically equivalent, so clearly both of these two statements are equivalent. So you can use one or the other. I personally find this one easier to use quite often, but it all depends on the context. So what does a one-to-one function look like, or an injective function look like? Let me give you an example of a function which is injective. Got this map. I'm going to take x1, x2, and then x3. And let's say y1, y2, and then y3. And send x1 to x2. We'll send x2 to y1, and then let's say x3 to y3. You can even add another fourth element here. It's in the codomain, but it is not in the range of the function. So this is an example of, if you call this here f is injective, right? Because every element in the domain is being sent to a unique element in the range. In other words, you don't have a scenario where you're seeing one element, right, being the image of two distinct elements in the domain. Let me draw here or give you an example of a function which is not one-to-one. Take the following function: x1, x2, x3, and let's have y1, y2, y3, and then y4. We call this g. X1 goes to y1, x2 go to y1, and x3 go to, let's say, y3. Right. So since f of x1 is equal to f of x2, and x1 is not equal to x2, then I want to use g, right? So let's do that. So g of x1 is equal to g of x2, but x1 is not equal to x2, then g is not an injective function. Okay, so we'll say that, so suppose let f be a function which is mapping x to y, where x is the domain of the function and y is the codomain of the function. We say that f is surjective or onto if the domain, if the codomain of f and its range are equal as sets. So here is an example of a function which is surjective. Notice that here is the range of the function, and it's also the codomain of the function. Call it f. So f is a surjective function. Now let's talk about what it means for a function to be bijective. A function is said to be bijective or a bijection if it is injective and surjective. In other words, a function which is one-to-one and onto is a bijection or a bijective function. Let us look at an example here. Let's suppose we have a function which is mapping the set of all integers into the set of all integers such that for every k which is an integer, we'll say that the image of k, f of k, is 3k. Okay, so now my aim here is to show that this function is injective. So I claim that f is injective. And let's prove that it is injective. Here is some scrap work. Let me show you some scrap work. This is not the official proof. So remember that to be injective means that if we want to show that if f of k is equal to f of n, then we want to show that k must be equal to n, right? So really we want to show proof here is an implication, and we can prove it directly. So we can start by assuming that f of k is equal to f of n. This is again scrap work. Okay, this is the part that the instructor doesn't see. All right, so you'll start by assuming that f of k is equal to f of n. Okay, so that means essentially that 3k is equal to 3n, and by dividing each side by 3, we obtain, so by dividing each side by 3, we obtain, of course, that k is equal to n, which is what we want. Okay, now that we understand exactly what we want, then we can come here and then write a correct proof, which is well structured. So let us follow the right format. We'll say, let us assume, again, this is a direct proof, that k and n are integers such that f of k is equal to f of n. By definition, or in other words, or as such, let's say as such, 3k must be equal to 3n. Now, dividing each side of the equation 3k is equal to 3n by 3 yields or gives that k must be equal to n. So therefore, the function f is injective. And we are done with our proof. So the map which sends every element, every integer to its triple is an injective map. Now I claim that f is not surjective. Again, scrap work. So to prove that f is not surjective, it suffices to show that its range is properly contained in its domain, in its codomain. It's properly contained in its codomain. Okay, so in other words, I have to find an element of the codomain which does not contain which is not inside the range of the function. Now, notice that the range contains all multiple of 3. So simply take, let's say, a number, an integer, which is not a multiple of 3, but which is an integer. Say, for example, 2. Okay, so that should give us the desired that should give us exactly what we want. So to prove this, proof, I'm going to actually prove this by contradiction. So let us assume by contradiction that f is surjective. In other words, therefore, the domain, the range of f must be equal to its codomain, which is the set of all integers. Okay, so now let's suppose let k be an element in take for example, let's suppose let 2 be an integer. Let 2 be a fixed let's say let's y be equal to 2, which is an integer. And by assumption, since 2 is in the range of f, there must exist some integer k such that 2 is f of k, which means that 2 must be equal to 3k. Okay? Now, as a result, consequently, if we divide each side by 3, we get 2/3 must be equal to k, and this means that 2/3 is an integer. This gives us the desired contradiction. We conclude that f is not a surjective function. Why? Because we were able to find an element in the codomain which is not in the range of the function. Now we will define the inverse of a function. So let us start as follows. Let f be a function between x and y, and assume that f is bijective. Then there exists a function, say g, between y and x such that g of little y is going to be equal to little x if and only if y is f of x. And we call such a function the inverse of little f, and we denote it by f inverse. Now, before I illustrate this, I want to be clear about this notation. This notation that we just wrote can be a bit confusing. So, as a remark, we must not confuse the inverse of f with the reciprocal or the multiplicative inverse. I want to call it with the multiplicative inverse, which is denoted by 1 over f. Okay, this is really important. This inverse here is not the same as the reciprocal. This is a function which is obtained by this characteristic. F inverse of y is x if and only if y is equal to f of x. Let me give you an example. Suppose we have this function here, say x1, x2, x3, and let's say y1, y2, and then y3. This is the domain and the codomain, and the okay. So let's map x1 to y2, x2 to y1, and then x3 to y3. So notice that this function here is an injective function. It's one-to-one. It's also surjective because the domain, the codomain, and the range of the function are exactly the same. Now, to define the inverse of this function, notice that we'll put y here. We need to reverse. So we'll have y here. We'll put y1, y2, and then y3. And x is here. x1, x2, and then x3. So the domain of of f becomes the codomain of its inverse, and its codomain becomes the domain of the inverse. And now y1 will go to x2, y2 is going to go to x1, and y3 is going to go to x3 because x3 was mapped to y3 under f. So this is f inverse. I've seen inverse functions in the past, especially when you were doing calculus and pre-calculus. So let me remind you of one way of computing the inverse of a typical function. Let's say let f be a function between the set of all reals into the set of all real, such that f of x is x cubed plus 3 for every x, which is a real number. Now, to compute the inverse of this function, you can set y to be x cubed plus 3. Now, you solve for x, so you get that x cubed is y minus 3, and then you take the cubic root. Right, so the inverse of little f is f inverse of y, which is y minus 3 cube root. Right, so that's, and the only reason why this was possible is because we started with a function which was in fact injective. It's bijective because its domain, its codomain, and its range are the same. So we started with a function which was bijective. So, and that's the reason why we're able to reverse the to compute the inverse of the function. Now, to show you that it is really important for a function to be injective, when one is interested in the inverse, let's look at this example. So, remark. In order for the inverse, okay, maybe for the inverse of f to be defined, it is crucial that f is injective. So here is a simple example. Suppose I have this function here, x, and then say y, and let's say this is my function. It's sending x1, x2, and then x3 are being sent to y. So this function f is not injective. So clearly it's not bijective neither. Now, if you try to find the inverse of this function, then you'll have to map y to which one? x1, x2, or x3. Right? And remember, for a function to be defined, you can only assign to every element in the domain exactly one element, right? One element cannot be mapped to two distinct elements. That's not a function, right? So the fact that f is injective, is not injective, this fact prevents us from defining the inverse of f. So, in other words, f does not have an inverse function. To summarize, again, it's really important. Non-injective function functions do not have inverse functions. Let f be a map between two sets. So f is a function. And let's E be a subset of X. The image of E is the set denoted f of e, which is the set of all elements of the type f of little x such that x is in E. Okay, so for instance, f of big X is the range of little f. Here is an example. Let's f be the following map. Let's say 1, 2, 3, and say 4, 5, 6. So suppose we have this map here. Okay. And let E be the set containing 1 and 2. Then clearly f of E will be the sets containing 4 and 5, right? Here is something a little bit less simplistic. Let f be a function between the set of all reals and the set of all reals such that f of x is 2/3 x plus let's say 2/3 x squared plus 5. Now let E be, let's say, the set 0, 1, which is essentially the set of all real numbers such that x is in between 0 and 1. Okay. Now let's compute the image of E. So x is in E if and only if we have this requirement which is satisfied. Now by squaring each side, we still get that x squared is in between 0 and 1, right? Because 1 square is 1 and 0 square is 0. Now we can multiply by 2/3. So we get 0 is less or equal to 2/3 x squared, which is less or equal to 2/3 times 1. And then we can add 5. So we get 5 is less or equal to 2/3 x squared plus 5, which is less or equal to 2/3 plus 5, which is 2/3 plus 15/3, and that'll be 17/3. So this means that if x is in E, if and only if 5 is less or equal to 2/3 x squared plus 5, which is less or equal to 17/3. So the image of E is f of E, which is clearly the sets, the closed interval 5 to 17/3. Here we'll talk about the concept of preimage. So let's f be a map, a function between two sets x and y. and pick, let's say Z be a subset of Y. So now this is a subset of the codomain. We say that the preimage of Z is the set. Now, please be careful with this notation, because I didn't tell you that F was injective, and I didn't say that it was bijective neither. So F inverse is not a function here, because the function may not be invertible. However, this is a notation which stands for the preimage of a set. Okay, so do not confuse this with the function F inverse, which may or may not exist. But in any case, the preimage of Z is the set of all little x which are in the domain, such that the image of x is an element of the set Z. Again, F may not be, so be aware. Since F may not be invertible, may not be one-to-one, or injective, it may not be invertible. Therefore, just the notation F inverse Z should be understood from context as a set satisfying the definition above. Okay. So here is an illustration. You have, let's say, this is X, and let's say this is Y, the domain of the function. Okay. And inside the domain of your function, let's say, suppose you have inside the codomain, let's say, suppose this is the codomain actually. Suppose this is my codomain. And inside the codomain, let's suppose we have a subset here, and this is Z. So this is your Z. Now, the inverse of Z will be the set F inverse of Z here, such that every element in here is mapped to an element in Z. That's what the preimage of Z is. Okay. Here's an example. Let's F be a function between the reals and the reals, such that f of x is equal to x squared. Now let's suppose that U is the sets 1, 2, and we want to compute the preimage of U. So since f of x is in U, if and only if 1 is less or equal to f of x, which is less or equal to 2. And this is the same as saying that 1 is less or equal to x squared, which is less or equal to 2. Then taking the square roots, we get 1 is less or equal to the absolute value of x, which is less or equal to square root of 2. And this will be the case if and only if x is in between negative square root of 2 to negative 1 union 1 to square root of 2. Right? So because of that, then the pre-image f inverse of u, which is f inverse of the set 1, 2, must be negative square root of 2 to negative 1 union 1 to square root of 2. Here's another example. Let f be a map between the integers such that f of k is equal to 5k for all integer k. Okay, so let's pick some elements. Let's suppose let I be 0, negative 5, the set containing 10, and then 20. So let's think of what can be, what is f inverse of I? Will be the set of all k in Z such that 5k is in I. Now notice that 5k is 0 if and only if k is 0. 5k is negative 1 if and only if is negative 5, I mean. If and only if k is negative 1, 5k is 10, if and only if k is 2, and 5k is going to be 20, if and only if k is 4. So because of that, the inverse of I consists of all points, of all integers of the type, this will be negative 1, 0, negative 1. I'm not ordering these numbers. Don't have to. It's just a set. 0, negative 1, 2, and let f be a function between x and y, and say g is a function between y and z. Be two functions. We define the composition function f composed with g to be the function, g composed with f, g composed with f is the function which is mapping x into z such that when we write g composed with f, then I have to tell you what it does to an element of little x. It's going to be g of f of x for all little x in x. Let's see that this makes sense. So if you have your set here x, so suppose this is x, y, and then let's say z. So if you take an element here, little x, it goes to f of x in y, And because G is defined on Y, it will take this element and will send it to G of f of x. Right, so this goes through f, and this here goes through G. Right, and the domain here is x, and the codomain is big Z. And so the point here that's important to say to note here is that the range of the composition G composed with F is the range of G. Is a subset, is a subset of the range of G. Okay, so we'll prove here that the composition of functions is actually an associative operation. So to this end, so let's f and let's say G be two functions. In fact, H into W be three functions. Then let little x be in big X. Then if we take F composed with G composed with H, let's look at this map here. What is that? By definition, this is F of G of H of X. But then this is F of G of H of X. Right? Okay, now let's look at F composed with G composed with H of X. Well, by definition, this will be F composed with G of H of X. And then by definition of F composed with G, this is F of G of H of X, which is F composed with G composed with H of X. Right, so this is true for all X. One can check that those two functions have the same domain and the same codomain, and they map every element in the domain to the exact same element in the codomain. So therefore, F composed with G composed with H is the same thing as F composed with G first composed with H. Right, so this is an associative operation. Now, it is important here to notice that composition of function is not commutative. Function composition is generally not commutative. What does that mean? This means that generally F composed with G is not going to be G composed with F in general. I mean that sometimes you see it, but you cannot guarantee that this will happen because it doesn't happen. I'll give you a counterexample. Okay, so here is a counterexample. Let's f of x be equal to x squared and g of x be 3x plus 1. It is easy to check that if f composed with g of x is 9x squared plus 6x plus 1. However, if you take g composed with f, you get 3x squared plus 1, and those two things are not the same, right? So although function composition is associative, it is not generally commutative. So order is important here. The order in which you compute your composition is very important. To the outcome. In this video, I'll talk about the identity function. What is the identity function? The identity function of a set will be a function that will denote it. Now I want to talk about the identity function of a set. So let X be a set, and let's I of X, or let's just call it I, be the map which is taking X to X, such that I of X is equal to X for all X in X. So it's the function which simply maps every element to itself. The identity function is the function that maps every element to itself. So I'll leave this as some exercises for you guys, some homework. Check that the identity function is a bijection, meaning that it is injective and surjective, and also check that the inverse prove that the inverse of the identity is itself, of the identity function is itself, and also prove that if we let f be a map between x and itself, then f composed with the identity function is going to be the function itself. In other words, for all little x in the set, f composed with the identity at x is going to be f of x. Okay, so these are good exercises for you. If I were you, I'll pause the video and just check very quickly, prove these results for yourself. Comments before we conclude this video. Very often, if we have many sets and many map, and we don't want to confuse which identity function we're talking about, if you have an identity function, let's say between y and y, will often denote it I sub y as shown here. Okay, just to avoid confusion.